In today's session, we are going to discuss on single source shortest paths. So this is the problem that is going to be solved by using greedy approach. And the optimal algorithm for solving this problem is the algorithm which is most popularly called as Djistra's algorithm. And this algorithm is going to apply greedy method to solve this shortest path problem. So you'll be needing a few basics regarding graphs. So if you see a graph will be consisting of nodes, one or more number of nodes. We can also call them as vertices, and these are represented using circles. So in this given graph, there are 4 nodes termed as 0, node 1, node 2, and node 3. And in this graph, there are 5 nodes named as node 0, node 1, node 2, node 3, and node 4. And two nodes in a graph will be connected by a link which is called as an edge. So the graph will be consisting of one or more number of edges, and every edge will be connecting 2 nodes in the graph. Now, depending upon whether these edges have direction or not, if these edges have a direction, then it's called as an directed graph, and an undirected graph will have edges with no directions. So you can see that there is a direction. That means you can traverse from node 0 to node 1, but not in the reverse way. You can traverse from node 0 to node 1. You can traverse from node 0 to node 2. From there, node 2 to node 3, you can traverse. But node 3 back to node 2, you cannot traverse. But whereas in undirected graph, if there is an edge between node 1 and 2, then you can traverse in both the directions. You can traverse from node 1 to 2, as well as from node 2 back to 1. And if each of this edge is given a cost, then it's called as a weighted graph, where every link in the graph will be given a weight. Then a path is the traversal of links through which you can reach from one node to the other node. It can either directly or indirectly. So that means if you have to start from node 0 and reach node 2, then you have to traverse from node 0 to 1, from node 1 then to 2. So there is an indirect path between node 0 and node 2. If there is a direct link that is connecting 0 to 1, then you can directly travel from node 0 to 1 using a single link. So that will be one hop. If you want to travel from 0 to 2, this has to take 2 hops. There can be multiple paths from node 0 to node 2. You can see this is one path traversing via node 1. You can also traverse via node 3. You can also traverse from node 0 to 4 to 3 and then to 2. So in total, if you have to traverse from node 0 to 2, there are 3 different paths. Now, given a weighted graph, you'll always choose the path with shortest distance, and the distance of this path traversing from 0 to 1, from there to 2. The distance of this path is the sum of the weights of the edges. So it is 3 plus 1. So that means if you are going to travel through this path, then the cost of the distance will be 4. If you are taking this path, then the cost of the distance will be 9. If you are taking this path, then the cost of the distance will be 13. So there are 3 different paths for traversing from node 0 to 2 with different weights, different costs of the paths. Always, whenever you have to traverse from a source node to the destination node, and there are multiple paths that are available, then you are always going to choose the shortest path. The shortest path is the one that has shortest distance between node 0 and node 2. Now you have all the basics regarding what are graphs, directed, undirected graphs, what are nodes, edges, what is a weighted graph, and what is the shortest path. Let us define the problem, single source shortest path problem. Now, single source is, you will be given a graph. A graph may be directed graph or it may be undirected graph, which may have one or more number of edges. You'll be given one source node. Among these 4 nodes, say for example, you will be given a node which is called as a source node. Now the problem is that you'll have to find the distance, you'll have to find the shortest path from the source vertex to all the remaining vertices. So you'll have to find shortest paths from node number 0 to node number 1. You have to also find shortest path from node 0 to node 2. Also find shortest path from node 0 to node 3. So among all the given vertices, one vertex will be treated as the source vertex, and the problem is to find the shortest paths from the source vertex to all the remaining vertices. So given a graph, this may be a directed graph or an undirected graph, and this graph contains a set of vertices V and a set of edges E, and also each edge will be weighted, that is each edge E will be associated with a cost, and among all the vertices, one vertex V0 will be treated as a source vertex, and the problem is to determine the shortest paths from the source vertex to all the remaining vertices in the graph. And the assumption is that all the weights must be positive. That is the assumption for the single source shortest path problem, or that will be the assumption for the Djisktra's algorithm. Dijkstra's algorithm will only work if all the weights in the graph are positive weights. It may not work, it may not produce an optimal solution if the weights are negative. So Dijkstra's algorithm is going to apply a greedy approach method, where the optimization measure will be the sum of the path. The optimization measure is the sum of the paths. And the objective function is that you have to generate the shortest paths. That means you are going to have to minimize the sum of the path lengths. That is, you will be generating multiple number of paths from source vertex to the remaining vertices, and each individual path must be of minimum length. So the single source shortest path problem is a minimization problem. This is a optimization problem where the objective is minimization of the path lengths. So it's going to work like this. For a given graph, using the greedy approach, if there are n number of vertices in the graph, then the greedy approach will be repeated for n number of times. So if I take this particular graph, the given graph shown here has 5 vertices, then the process will be repeated for 5 times. And in each step, the process goes like this. Assume that 0th vertex, the 0th vertex is the source vertex. That means from V0, I'll have to generate shortest paths to all the remaining vertices. Now, what will happen in step 1? What will happen in step 2 and so on? For that, the process will go like this. First, a shortest path to the nearest vertex is generated. That is, you are going to consider the source vertex. And in step 1, you are going to generate a shortest path to the nearest vertex. Then step 2, you are going to consider another nearest vertex and you are going to generate another shortest path. And after n number of steps, shortest paths will be generated from source vertex to all the remaining vertices. Now, how I can call this as a greedy approach? This process I am taking here, you can see every time I'm going to select a vertex that is nearest and I'm going to generate a shortest path. So in every step, I'm going to make a selection using greedy approach that among all the vertices that are available, I'm going to select such a vertex which is nearest, ante to whom the distance is shortest. So I'm making a greedy choice in every step, and hence the Djisktra's algorithm is said to follow a greedy approach, and hence it is a greedy algorithm. So here, if I consider vertex 0 as the source vertex, then find out from vertex 0 which are all the remaining vertices that you can reach. So you can observe here, vertex 0 is connected to vertex 1 directly. It is also connected to vertex 3. It is also directly connected to vertex 4. Now I consider among vertex 1, 3, and 4, I'll have to make a greedy choice. I have to select a node which is nearest to vertex 0. That is, the distance from 0 to 1 is 3. The distance from node 0 to 3 is 7. The distance from vertex 0 to 4 is 8. So among these 3 nodes, 1, 3, 4, which is the vertex that is nearest to vertex 0? That is vertex 1. So I'm going to generate in step 1 the path V0 to V1. So I have taken this path V0 to V1. Now from V1, now this is your current path, current vertex. Now I'll have to select from vertex 1, I have to consider it as source. Now check who are all connected to vertex 1. Vertex 1 is connected to 2. It is also connected to 3. Now next vertex that I have to select is the one which is nearest to vertex 1. So among the vertices 2 and 3, if I check their distances and compare the distances, the distance between vertex 1 and 2, the distance between vertex 1 and 3, I'm going to compare. Then I can see that vertex 2 is the one that is nearest to vertex 1. So the next node, the next vertex that I'm going to select will be vertex 2. And the path I have generated is V0, V1, V2. So in such steps, I'll repeat these steps for 2 more times. And at the end of all the 5 steps, you will have with you the shortest paths from vertex 0 to all the remaining vertices. So the steps here, in order to generate the shortest paths, the steps will be, you are going to select the vertex which is nearest to the current vertex, and you are going to generate a shortest path to this vertex. So this is your Djisktra's algorithm. Given a graph G which contains vertices and edges, considering the source vertex to be V0, Djisktra's algorithm will determine the lengths of the shortest paths from source vertex to all the remaining vertices in the graph. And Djisktra's algorithm works on both directed and undirected graphs, but this algorithm will not work when the graph consists of negative weights. So before proceeding for working out an example problem using Djisktra's algorithm, you'll have to know this technique which is called as relaxation of vertices. So for simplicity, I have taken here a very simple graph which contains only 3 nodes, node 1, node 2, and node 3. And the edges are weighted. The distance from node 1 to 2 is 4. The distance from node 2 to 3 is 5. Now consider in step 1, I'm going to fix the distances of node 2 and node 3. And I'm going to consider that vertex 1 is the source vertex. Now I have to generate shortest paths from vertex 1 to 2 and shortest path from vertex 1 to 3. And for that, here I'm going to represent distance of 2, and here the value will be distance of 3. And this value, distance of 2, is the value that indicates the distance from the source vertex to node 2. Okay, so there is a direct path from vertex 1 to 2 and the distance is 4. Now the distance is 4. From vertex 1 to vertex 2, the distance is 4. Now, there is no direct link, there is no direct path from vertex 1 to vertex 3. So initially, I am going to consider distance is infinity. Distance is infinity. Now, the next step will be considering the nearest vertex to vertex 1. So vertex 2 is nearest to vertex 1. So once a vertex is selected, you will have to try and apply relaxation for the remaining vertices, which are connected to vertex 2. Now, how to apply relaxation procedure? So take vertex 2 now. Check what are all the remaining vertices that are connected to 2 and try to relax them. So to vertex 2, there are 2 vertices that are connected. Vertex 2 is connected to vertex 1. Also, it is connected to vertex 3. Now, do I have to apply relaxation procedure on vertex 1? No, I'll not be able to apply relaxation on vertex 1 because vertex 1 is already visited, right? So in the Dijkstra's algorithm, in any step, there will be nodes which are already visited. There will be nodes which are not visited. So at this particular point of time, node 1 and node 2 are already visited nodes. You can apply relaxation procedure only on unvisited nodes. So even though vertex 2 is connected to vertex 1, but you need not apply relaxation procedure on vertex 1 because it is already visited. Now, vertex 2 is also connected to vertex 3. So now I have to apply relaxation procedure on vertex 3. So now what I am going to do is I am going to consider this as U and this as W. And I'm going to apply this relaxation procedure. If this condition is true, you are going to update the distance. Okay, so now what I'm going to do is I'm going to calculate distance of U plus distance of U plus cost of the edge from U to W. If it is less than the distance of W, then I'm going to update the distance of W. That is, you have to perform addition of distance of U plus cost of the edge between U and W. That is, I have to add 4 plus 5. 4 is the distance of node 2. 5 is the cost of the edge between U and W. So distance of U, so distance of vertex 2 plus the cost of the edge between node U and W. These two you have to add. So I have added 4 plus 5 and the result is 9. Now I have to check 4 plus 5. Is it less than infinity? Yes. Distance of U plus the cost of the edge between U and W is less than the distance of W. So I am going to update the distance of W. Now the new distance of W will be equal to 9. So I'm going to update the distance of the W node. So this is the relaxation procedure, which is one of the techniques used in Dijkstra's algorithm to update the distances of the vertices. So using this, we'll work out a problem. So this is an undirected graph that is given. Using the Dijkstra's algorithm, find the lengths of the shortest paths from vertex 1 to all the remaining vertices in the graph. So that means vertex 1 is to be considered as the source vertex, and applying the Dijkstra's algorithm, you have to determine the lengths of the shortest paths from vertex 1 to the remaining vertices in the graph. So I'll start working out. So this is your step 1. Source vertex 1 is considered as the source vertex. Now try to determine the distances for all the remaining nodes. So the distance will be either a value or it will be infinity. If there is a direct link between source vertex and the other node, then the distance will be equal to the cost of the edge. This is because there is a direct link connecting vertex 1 to 2. So take this value 4, the weight of the edge. That will be the distance from vertex 1 to vertex 2, which I have represented here. Now check from 1 to 4, there is a direct edge connecting whose weight is 7. So that means the distance from 1 to 4 is equal to 7. Now the remaining vertices I consider vertex 3, but source vertex is not directly connected to vertex 3. Hence, its distance will be infinity for now. In this step, the distance from 1 to 3 will be infinity. In the upcoming steps, that distance will be updated. Now, from 1 to 5 also, there is no direct path. So the distance of 5 will also be taken as infinity. This is step 1, where you are going to determine the distances for all the remaining vertices. If there is a direct edge from source vertex to vertex V, then that weight you take it. Otherwise, if there is no direct link, then you take the weight as infinity. Then we'll go to step 2. Step 2, as I said, we are going to make greedy choice. We are going to check which are all the nodes that are there, which are not visited. Now I can say that this node 1 is already visited. Now consider all the nodes which are unvisited and find the node that is having shortest distance. So I have these nodes with distances 4, infinity, 7 and infinity. Among all these 4 nodes that are unvisited, select the node with shortest distance. That is, here I am making a greedy choice. So now once I have selected vertex 2, it becomes visited. Then immediately you are going to update the distances of the remaining nodes. That is, you are going to apply the relaxation technique. Now to apply relaxation technique, you have to check what are all the vertices that are directly connected to node 2. Now node 2 is directly connected to node 1, but because node 1 is already visited, you need not apply relaxation procedure. Then Node 2 is also connected to node 3. It is also connected to node 5. These two are unvisited nodes. So apply the relaxation procedure on node 3 and node 5. Applying the relaxation procedure, for that you'll have to make some calculation. And the calculation is, you have to sum 4. You are going to add with 5 and check if it is less than the current weight of node 3. Right? So the procedure is perform addition of the distance of node 2 plus the weight of the edge connecting node 2 and 3. Check if it is less than the distance of node 3. If this condition is true, 9 is less than infinity, then immediately you are going to update. You are going to update the distance of node 3, and the new distance of node 3 will be 9. Now, in the same way, I'm going to apply relaxation procedure on node 5. For that, you have to perform addition of 4 plus 6. The value is 10. 10 is less than infinity. So I'm going to update the distance of node 5. This is your step number 2. Now, going to step number 3. Now, your current node is 2, which is already visited. Now, in step 3, you have to select another node from the list of unvisited nodes. Select the one which has shortest distance. Now, the distances of the unvisited nodes are 7, 10, and 9. Now, select the node with the shortest distance. That is, I am selecting node number 4. Now, once a node with the shortest distance is selected, apply relaxation technique. Now, for applying the relaxation technique, check what are all the vertices that are connected to 4. So node 4 is connected to node 1, but this is already visited, so I will not apply relaxation technique. Node 4 is also connected to node 5. I'll have to apply relaxation on node 5. Now, whether I have to update the distance of node 5 or not. For that, I'll have to perform addition of 7 with 1. 7 plus 1 is 8. 8 is less than 10. So I'm going to update the distance to 8. I'm going to update the distance to 8. Now, again, step number 4. Step number 4, among all the remaining unvisited nodes, select the node with the shortest distance. So among 8 and 9, the shortest distance is 8. So I'm going to select node 5. Once it is selected, it becomes visited. It is now a visited node. Now try to apply the relaxation technique. For applying relaxation technique, check what are all the nodes that are connected to 5. Node 5 is connected to 4. It is already visited. Node 5 is connected to node 2, which is already visited. Node 5 is also connected to 3. Now I have to apply relaxation on this node 3. Now for that, I'll have to check whether I can relax or not, relax node 3 or not. For that, I have to perform addition of 8. What is the distance of node 5? 8 plus cost of the edge between node 5 and node 3, which is 6. So I'm performing addition of 8 plus 6, which is 14. 14 is not less than 9. So I'm not going to update the distance of node 3. No updation will be done. Now the last step, 5th step, there is only one node that is left unvisited. So that itself I'll select and I'll try to apply relaxation procedure. Node 3 is connected to node 2, which is already visited. So I'll not apply relaxation. Node 3 is also connected to node 5, which is already visited. So no need of applying relaxation. Now, after 5 steps, you can see that all the 5 nodes are visited and each node is associated with the shortest distance. Now, how to know what are all the shortest distances? Source vertex is 1. From node 1, the distance to node 2 is 4. From node 1, distance to node 3 is 9. From node 1 to 4, the distance is 7. From node 1 to 5, the distance is 8. And these are all the shortest distances from the source vertex to all the remaining vertices. Now I'm going to prepare a table. Once this is done, I'm going to prepare a table. What is the vertex and what is the distance of the vertex? Considering the source vertex to be V1. Now the remaining vertices are 2, 3, 4 and 5. And the distances are 4, 9, 7 and 8. And all these are shortest distances. From vertex 1 to vertex 2, the shortest path available is with distance 4. From vertex 1 to vertex 3, the shortest path is available with the distance 9 and so on. So this is how, given a problem, you are going to apply the Djisktra's algorithm and you are going to find shortest distances from source vertex to all the remaining vertices. So whatever the procedure that I have discussed till now, and this is the final table that we have prepared. And instead of in the pictorial representation, we will have to tabulate it. This is how you are going to tabulate. The process goes like this. Initially, what did I do? Given the particular graph and considering that this is the source vertex, I have selected this vertex. Then I have determined the distances, the initial distances, step 1 low. The distances were 4, 7, infinity and infinity. So the same things are tabulated here, 4, infinity, 7 and infinity. These are the distances from node 1 to node 2, 3, 4 and 5. Initially, there are no visited nodes. Now step 1, I have selected node 1. So it is visited now. Now I am going to select among all the unvisited nodes. I have to select one node which is shortest. So I will select node number 2. I have selected node number 2, which is the nearest node to node 1. Now, from node 2, I am going to apply the relaxation procedure and I am going to update the distances. So I have updated the distances as infinity is changed to 9. This infinity is changed to 10. So in the same way, 4 infinity, 7 infinity. I have selected second node as the shortest node. Now 2 has become visited and I have applied relaxation procedure and I have updated the distances. This infinity I have updated to 9. This infinity I have updated to 10. Then among the remaining vertices, I am going to select the vertex with the shortest distance 7. So this is 4 I have selected. So now 4 will become visited. Now I'm going to apply relaxation procedure and I'm going to update the weights. So 10 I have updated as 8 in this step. So you can see here the updated weights 4, 9, 7, 8. Next I have selected node 5. Now node 5 will become visited. Apply relaxation procedure and update the weights. Then I have selected node number 3. Now node number 3 has become visited. Apply relaxation procedure and update the weights if necessary. And this will be your final weights 4, 9, 7, and 8. And this final table that I have formulated. This is how you are going to solve a problem using Djisktra's algorithm. This is the algorithm, Djisktra's algorithm for finding the shortest paths. You will be given vertex V. Vertex V, you have to take it as the source vertex. Then you will be given the set of weights for all the edges in the graph. Then N will indicate how many number of vertices are there in the graph. Distance is the array that you have to fill up with the shortest distances. So input will be V, which is the source vertex, all the weights of the edges and how many number of vertices will be there. That will be the input to the Djisktra's algorithm. The output of the algorithm will be distance vector, the distance vector that you have to formulate. Initially, all the nodes will be unvisited. All the unvisited nodes will be represented with a value false. A visited node will be represented with a value true. Here you are going to initialize the weights, initialize the distances for each vertex. Then you are going to repeat steps 2 to n minus 1. That is, every time you are going to generate a path, and if there are n number of vertices in the graph, you are going to generate n minus 1 paths. Once you have selected a node U with the shortest path, it will become visited. Select a node which have shortest path and make it as visited. Now check what are all the nodes that are adjacent to U. And if necessary, apply the relaxation procedure. Repeat this process for n minus 1 number of times. And once this is done, you'll have a distance vector that will present the shortest distances from source vertex to all the remaining vertices. Now the time complexity of this algorithm is big O of n square because you are not considering this loop, initialization loop, you are not analyzing, you are only analyzing this part, and this part has 2 loops, and hence the time complexity of the algorithm is big O of n square. But you can reduce the time complexity of the Djisktra's algorithm to n plus e into log n. Now, this reduction in time complexity is possible if you are maintaining V minus S in the form of a red-black tree. Here I am maintaining in the form of an array. Instead, if you are maintaining this V minus S data in the form of a red-black tree, then you can reduce the time complexity to n plus e into log n, where n is the number of vertices, e is the number of edges. Okay, so in this session, I have discussed what is single source shortest problem, what is relaxation technique, and I have presented the algorithm for the Djisktra's algorithm. Then I have also worked out a problem. Given a graph, how to find the shortest paths using Djisktra's.